glass dome desalination for desert afforestation, agroforestry and agriculture projects. There are many ways to desalinate water in dry areas and deserts. Desalination is crucial to water security in many regions that are impacted by climate change and rising temperatures. Nobody knows if there will be enough water in most of the world soon. Without water, life cannot go on, farming fails, industries shut down, cities become unlivable. For this reason, water security is associated with global security and welfare. Some of the desalination systems are shown next. Reverse osmosis efficiency improvements. Reverse osmosis is the most widely used desalination technology. Ongoing research focuses on improving the efficiency of reverse osmosis membranes, which involves developing better membrane materials, optimizing membrane structure, and reducing fouling and scaling issues. These advancements aim to enhance the productivity and energy efficiency of the desalination process. Forward osmosis. Forward osmosis is an alternative desalination technique that utilizes an osmotic gradient to draw water through a semi-permeable membrane. Forward osmosis has gained attention due to its lower energy requirements compared to reverse osmosis. Ongoing research focuses on developing better draw solutes, improving membrane performance, and exploring hybrid forward plus reverse osmosis systems for enhanced desalination efficiency. Membrane distillation. Membrane distillation is a thermal-driven desalination process that utilizes a hydrophobic membrane to separate fresh water from saline water. Research efforts are aimed at developing more efficient membranes with higher permeability and selectivity, as well as optimizing the energy consumption of the process. Graphene-based desalination. Graphene, a single layer of carbon atoms, has shown promise in desalination research. Graphene-based membranes have excellent water permeability and salt rejection properties. Ongoing studies focus on scaling up production, improving membrane stability, and reducing production costs to make graphene-based desalination commercially viable. Solar desalination. Solar desalination utilizes solar energy to power the desalination process. Researchers are exploring various solar-driven technologies such as solar stills, multi-stage flash distillation, and solar-powered membrane processes. Advances in solar desalination aim to reduce energy consumption and make desalination more sustainable. Electrodialysis and capacitive deionization. Electrodialysis and capacitive deionization are electrochemical desalination technologies. Electrodialysis employs ion exchange membranes and an electric field to remove ions from water, while capacitive deionization uses porous electrodes and electrical potential to remove ions. Ongoing research aims to improve desalination efficiency, optimize system design, and enhance the energy recovery of these processes. The basic idea behind the artificial desalination process is simple. The procedure is taking fresh water from the ocean, filtering off the salt, and distributing it to other areas, mostly for use in agriculture or by people. Nevertheless, there are substantial financial and environmental consequences associated with both strategies. Owing to the high energy requirements of desalination, there were related financial costs and possible global environmental effects depending on the energy generation process. In most parts of the world, fossil fuels are the subject of this. Desalination plants are predicted to create 76 million tons of CO2 yearly. This figure is expected to have climbed by over 3 times by 2040. Locally, the main issue is caused by hypersaline brine. The brine is frequently poured back into the ocean once fresh water has been removed. Because it is much denser than seawater, which may damage ecosystems by raising salt concentration and decreasing oxygen levels, it sinks to the bottom. It all comes down to desalination. The number of saltwater desalination plants in operation globally has more than doubled since the early 2000s. Today, more than 300 million people worldwide receive their water through this method. The countries are facing issues due to the massive amounts of waste produced by this energy-intensive industry. With current reverse osmosis technology standards, 2 gallons of salt water may generate 1 gallon of pure water. Brine is pumped back into the ocean, leaving a gallon behind. All of this, though, is intended to alter The answer is supposedly in a cutting-edge technology that resembles this, an approximately equal-sized cauldron covered by a sphere made of a glass and steel dome that rises to a height of 25 meters. The so-called solar dome was created by UK-based firm Solar Water in collaboration with Cranfield University. Its underlying notion is actually fairly straightforward. A glass-enclosed aqueduct system is used to flow seawater into the dome, supplying it with sunshine along the way. The sun's energy is focused onto the dome by a series of parabolic reflectors. This caused the seawater in the cauldron to evaporate more quickly. As a result, very pressurized steam is released, and when it condenses, fresh water is created, which is subsequently piped to reservoirs and irrigation canals. The solar dome can produce 30,000 cubic meters every hour at an astonishingly cheap cost of 34 cents per cubic meter. It has no carbon footprint at all. Still, the issue of the hypersaline brine does not go away. It is thought that the desalination process in NEOM reduces the total amount of salt created during water extraction by not releasing any brine into the ocean, helping to prevent harm to marine life. Still, the topic of what truly happens to concentrated brine remains unanswered. It is feasible to extract it and sell it for a profit, claims Solar Water. The brine contains certain elements that are used in a variety of industrial processes. It is still up for dispute if this is a true effort and whether the concept of developing a financially sustainable extraction of resources for other industries will succeed. Construction is now underway on the first solar dome to facilitate industrial experiments. When it comes to creating safe and sustainable freshwater supplies for the environment, other water-scarce countries might take a cue from the NEOM solar desalination project. Solar Water has set the lofty aim of carbon-neutral agriculture and reforestation in the middle of the desert. How much of this vision materializes is hard to predict. NEOM will surely put it to the test when the first solar dome desalination plant is built, which is expected to happen soon. Notwithstanding all of its issues, desalination is a sustainable method. It is anticipated that the industry would grow as costs decline and the likelihood of a water scarcity rises, and the countries of the Middle East will rely solely on it. It is our shared duty to manage the limited freshwater resources in a sustainable and environmentally responsible manner. We must also utilize our knowledge and creativity to identify the least harmful and most environmentally sound way to provide it.